Get started. Hi, everyone. Welcome back. Hope you had a good lunch. So really excited to have Hedyeh and Beyhaghi to speak. So Hedyeh is an assistant professor at the Manning College of Information and Computer Sciences at UMass. Her research spans algorithmic game theory and mechanism design, ML theory, and algorithms under uncertainty. She received her PhD in CS from Cornell and held postdocs at TTIC, Northwestern, and CMU before joining UMass. And today she's going to talk about active, noise-tolerant, and strategic online classification. Let's welcome her.
Thank you so much for the introduction. This talk is based on joint work with Saba Ahmadi, Nina Balkan, Avram Blum, and Kezia Najita. Saba, Avram, and Kezia are at TTI Chicago, and Nina is from CMU. This talk is mainly motivated by machine learning algorithms being increasingly used for decision making. So on the left, we have a symbolic picture related to loan or credit approval. And on the right, we have a picture about automated resume screening, which could be used, for example, for hiring purposes or for admissions to higher education. In both of these scenarios, we are dealing with people or participants who care about the outcome of these decisions. So for for loan or credit approval, the applicants want their applications to be approved. And in the second example, the students want to go to their dream jobs, to their dream colleges, or get their dream jobs. Okay. In order to achieve their goal, these applicants may take actions to change their information and may provide different information from the true reality to the process. For example, in the loan or credit approval, the applicant may just open up some new credit cards right before their application, or they may borrow some money and pay off the debt that they had. And in the second example, the students may take GRE or may take test preparation courses or may retake exams like GRE or SAT multiple times to increase their chances. Okay. In many scenarios, these actions are not actually changing the true qualifications of the people, and they are like mere adaptation and manipulation to the algorithms. For them to appear to be qualified. And these actions do not always change the true qualifications of these applicants. The main problem that we have in this setting is if we use classic learning algorithms that ignore the strategic behavior of agents, this may result in poor performance and the decisions made may even be incompatible with the goal of the algorithm. Okay. And we saw some examples of, for example, strategic aspects in the first talk of the workshop by Eric. And our main goal in this area is to propose ways to adapt these algorithms to strategic behavior. And we want to make these algorithms robust to manipulation. This topic of classifying agents who have incentives or are strategic have been a hot topic recently, and there are many papers that studied this topic from different angles, like accuracy, fairness, incentivizing efforts. I'm going to mainly be talking about two papers, and both of them are mostly in the first category. So I'm going to start with a joint work with Saba, Avram, and Kezia. Okay, so let me give you our model or interaction protocol at each point in time. So we're going to run this over time. And at time t, our algorithm is going to announce some qualification rule. Okay, so this could, for example, be the bank that sets its qualification criteria. Or it could be the school that sets its admission policy and announces this. In the next step, an applicant is going to show up. We assume that the applicant has some true features. We call them original features denoted by XC or H. And these applicants may take some actions to modify these features to appear to be somewhere else. We denote their modified features by X mod. Okay, so these applicants have some utility functions. So we assume that these applicants receive a benefit of 1 for being classified as positive, minus the cost that they have paid to move from their original features to their modified features. We assume that the original data points are linearly separable. So technically, there is a weight vector that has positive dot products with truly qualified applicants and negative dot product with truly unqualified applicant. And there's a margin of separation between these two groups. The algorithm is going to decide positive or negative, is either going to approve or not approve the applications based on the observed features, based on X mod. Okay, so the algorithm had our learning algorithm, which was also the decision maker, had some qualification rule in the first step. So they're going to use that rule that they have set with the features that they see from the applicants and decide if they're going to take them or not take them. After this classification is done, the algorithm is going to learn the true label. So for example, it's going to learn whether the person who got the loan really paid it off or not, or the person that they've admitted for college or for the job, if they became really successful or not. Okay. And the algorithm is going to update its rule if it makes a mistake. Okay, so something I should maybe say now is I'm going to talk about 2 papers, and this is the assumptions for the first model. And in the second model, we are going to relax some of these assumptions. Okay. And our goal is to minimize the number of mistakes that we make over time. Okay, so kind of independent of the number of samples we are seeing, we want to say that there is this upper bound on the total number of mistakes that we can make. Any questions about the model before I move on? Okay. Feel free to interrupt with questions at any point. Okay. So if we have, with the properties that I showed on the previous slide, if we do not have a strategic behavior from the agents, classic learning algorithms like the Perceptron algorithm can learn the true classification and classify everyone in a good way and make a bounded number of mistakes. Okay, so it means that there's an upper bound on the total number of mistakes that this algorithm could take. I have the algorithm here as a reminder for people who are familiar with. If you're not familiar, it's not too important. The only important part about this algorithm is that there is some weight vector W that the algorithm is going to work with. Okay. So at each point in time, it's going to take some feature vectors that we have XT. If we have a positive dot product, the algorithm is going to classify positive, otherwise it's going to classify negative. And whenever the algorithm makes a mistake, it's going to update its classification rule by either moving towards the point or moving away from the point. Okay, so if it was a positive point that we had made a mistake, we're going to move towards the point by adding the feature vector of that point to the current weight vector. Otherwise, we're going to move away from the point by subtracting the feature vectors from the current classifier. Okay. Next, we're going to see that if we run this classic algorithm in a case that people are really strategic, it's going to make unbounded number of mistakes. It's going to do very badly, and it's never going to converge to a perfect classifier, even though one exists. Okay. So here we have some linearly separable data. We have some positives and we have some negatives. We are in a 2-dimensional space. So you can think of it, for example, as maybe the total amount of money a person has in their banks and their total amount of credit lines. Okay. So we have these two positive points and one negative. Okay, so first, let's say that this positive point shows up, and the algorithm is going to update its rule based on this point. Okay, so that's the very first step. Next, the negative point is going to show up. Okay, so this negative point, so basically this, I show the classification rule by this purple line. This vector means that anyone who is to the right of this line is going to be classified as positive, and anyone to the left is going to be classified as negative. Okay. And this is the current classification rule, and this negative point just wants to show up. Okay. So this point wants to be classified as positive, right? They want to like get the loan. Okay. But if they do not change their features, they're not going to be approved. So what they're going to do is to move a little bit to the classification boundary to be classified as positive. Okay, so in this example, I'm assuming that there's a cost of 2 per unit of movement. Okay, so it means that like for like any one movement, people are going to pay a cost of 1. And we already know that they get a benefit of 1 for being classified as positive. Okay. So this negative point is going to show up, is going to move their features, and they're going to actually pretend to be here. Okay. The algorithm is going to only see this person as here. They do not know their true features. So based on this classification rule, the algorithm is going to classify them as positive. Okay. And if we classify this person as positive, right after that, we realize that we have made a mistake. This was actually a negative, like a non-qualified person, okay? So if we follow the classic Perceptron's algorithm to do our update rules, we are going to move away from that point by subtracting the features that we saw from our classifier, okay? So this new purple line is going to be our new classifier, okay? Next, this positive point comes to the game. This point also wants to be classified as positive, okay? But with the current classifier, it's not classified as positive. They're on the wrong side, okay? But this point is too far away from the classifier. So if this person kind of pays all these costs to manipulate, they have paid like more costs than their gain. So it's not worth it for them to move, okay? So this person is going to stay where they are, and they're on the negative side of the classifier, so they're going to be classified as negative. And the next thing is like we learn about their true label and we see that they were truly positive. We have made a mistake. So again, we're going to update our rule. Okay. But if you look at like where these points are, this is exactly where the negative point pretended to be. Okay. So we saw like a negative point here, and right now we're seeing a positive point here, and we've again made a mistake. So we're going to shift back to where we were. Okay. So basically, if these 2 points show up over and over again, we're going to oscillate between these 2 linear classifiers that I just showed you, and we're going to make unbounded number of mistakes. Okay. Any questions about the setup? Yes.
Do we assume that these negative points know where the boundary currently is?
Yes, exactly. That's a very important assumption. We assume that like our learning algorithm announces its current qualification rule. Yeah, good point. Yes.
We need to consider similar examples where the minus in the class are not exactly in the same place, but there is a small gap or something.
Right. Yes. Yes. This is not only, yeah, it's just an extreme example, but you can tweak things a bit and still this unbounded number of mistakes hold. Okay. All right. So the classic Perceptron algorithm in this case makes unbounded number of mistakes and never converges to a perfect classifier, although one exists. Okay. So sorry, this was still the oscillating part. Okay. So I claim that this purple line and this picture is actually a perfect linear classifier for my strategic setting. Okay, why is that? So the negative point is on the negative side of the classifier, and they're too far to move to the classifier. Okay. This positive point is already on the correct side. They're going to be classified as positive whenever they show up. And this other positive point can move a little bit and get on the classifier and be classified as positive. Okay, so in this example, the negative points are too far, like they are not going to manipulate. And the positive points are already on the correct side, or they can move their features and become on the correct classifier, be classified as positive. Okay. Okay, so let me maybe explain a little bit about the utility functions of the agents, and this is going to be useful as we go on to present our ideas of how we adapt this algorithm. Okay, so as I mentioned, the individuals report X mod based on their true original features and also the current boundary of the algorithm, the classification rule of the algorithm. We assume that their utility is defined as the value that they get for the modified features minus the costs that they make to move from their original features to the modified ones. Okay. And one way to define this cost model is a linear cost model is a Euclidean norm of the distance between the original one and the one that they're going to find. Okay. So basically, they're going to, these participants or these individuals are going to get a value of 1 if they're classified as positive and 0 if they're classified as negative. To maximize this utility, they're going to take the least costly action, okay? So either if they find some action so that their cost is less than 1, they're going to take it, and they're always going to take the least costly action possible. Okay, so let's think about it in a picture. So I'm now getting to how we use these ideas to adapt the algorithm. So one of the main ideas that we use is to utilize this knowledge about the strategic behavior of the agents. Okay, so let's say this is the classifier that we are using. Okay. Basically, the agents are going to manipulate or move their feature if they are close enough to the classification boundary. Okay. If they are, and particularly if they're on the negative side, sorry, and they are within a margin. Okay. So if they are to the right side, they do not need to classify. If they are to the left of the margin, it's too costly for them to move. Okay. And particularly the length of this margin is 1 over the cost, because that's exactly the point where their utility is, their gain is going to be equal to their cost. Okay. Another point is to maximize their utility. These individuals are going to take the least costly action, as I mentioned on the last slide. So it means that they move in the best direction and they move the least amount possible. Okay, so when we have linear separators, our applicants are going to move perpendicular to that separator. Okay. So how are we going to use that? So our main result is a perceptron style algorithm that still makes a bounded number of mistakes. And we are mainly making 2 changes to the original algorithm that I presented. So let's think that we're in this hypothetical scenario that we know the actual true classifier. Okay, so this is not actually the case, but let's imagine for a second. And let's say this gray line is the actual class, the best classifier if we did not have strategic behavior. Okay, I'm going to claim that if we shift this classifier by some amount, exactly by the amount that the agents can move, and I get this purple line, this is the perfect classifier if we have strategic behavior. Okay, so the main reason is that the positive points are already, the negative points are on the negative side of the new classifier, and it's too far for them to game. And the positive points, as you see in the picture, are already on the correct side or can move to this side, can move to the classifier and still get non-negative utility. Okay, so that's the first idea. If we know the perfect classifier, we know that we can just shift it, and that will be the perfect classifier in the strategic setting. But of course, we don't know the perfect classifier for the non-strategic set, for like even for the true data, and that is like something that we're trying to learn throughout the algorithm. So this brings us to the second idea that we use with the algorithm. And the second idea is, instead of using the features that we see of these points to use in our update rule to like change our classification rule based on the point that we see, we're going to use proxies for the point that we see. Okay, so we know, for example, that this point has, if we have a manipulated point, or even if we do not have the manipulated point, we have some idea of their region, of the potential region of their true features, okay? So we can use our knowledge of the region of the true features and pick a point. So it's not a trivial thing, but I'm not going to go into detail about it. We can find proxies and use these proxies in our update rule. Okay, so these are the main two changes that we're going to make to the algorithm. And these proxies need to be chosen carefully because we want to make sure that we're always updating our classification rule in the right direction. And we also want to make sure that we're making enough progress for convergence. Okay, so let's look at the algorithm, see how it changes. The first part of the algorithm is very similar to what we had before. So we're going to predict positive until we make a mistake. After we made our first mistake, we're going to shift the classifier as I showed you. So basically, we're going to raise the bar for classifying people as positive. So no longer a positive dot product is enough. We're going to have a strictly positive dot product for this classification. Okay, so that is the first change. And the second change is to use proxies instead of updating with the actual features that we see. Okay. This algorithm is specifically written for L2 costs, but we can extend it to L1 costs as well, for example. And we can also modify it to work in a setting that we do not know the cost of manipulation. Okay. So here are our results in the setting. We show that if we use this strategic perceptron algorithm, there is an upper bound on the number of mistakes. So let me tell you a little bit about these parameters. So R is like the amount that strategic agents can move, the maximum amount. Big R is the largest length of a point, and this gamma is the margin of separation. Okay. And if you want to compare it with the original perceptron algorithm, the only changed factor is this little r. Okay, so like in the case that r is 0, we exactly match the previous bounds. Okay. And this also extends to other cost settings. And whenever we do not know the costs, the bounds are still not too different. Okay. Any questions about this part before I move on? Yes.
Yes, I'm curious about so this sort of maximum movement that they can do. When I'm trying to analogize this to the real world, it's saying there's a certain amount that you can alter your resume. Why is it that there should be an amount of cost for something in that setting? Like for changing my resume, I could just completely lie about it.
Right. Well, so you're right. Like, well, maybe you can say that like if you change it too much, like they're going to figure out, for example, you know. So that could be like one way to think about it. Another way is like if you are taking, or if someone is taking, for example, test preparation courses, then there is kind of a limit on how much they can spend. So like some of these actions are costly. So that's like one way to think about it. And for some of the other actions, we can think that if you change too much, maybe they'll figure out.
One more.
Yeah.
It seems in the algorithm that you're proposing here, you sort of implicitly make the assumption that everyone is going to lie to some degree, or that you can be strategic by lying even if you are a positive point. That feels like that may be unfair then to points that don't lie. There would be bias against them.
Right. Yes, that's a good point. Like I think behaviorally it could happen. Maybe like people really like even people who have good resumes really like try to make it polished and everything. But maybe like people have different costs for these movements or altering, and that could like bring a fairness aspect. Yeah, great point. Okay. So that ends the part about the first paper. Now I'm going to shift to a second paper, joint work with Nina. Okay, so in the setting that we have seen so far, we have assumed that the outcomes are immediately available to us. Okay, so we're going to make this classification, and right after that, we're going to figure out if, for example, this person that we've admitted for college has become successful or not, or this person that we've given loan to has repaid their loan or not. Okay, but in many real world applications, these labels or these like actual outcomes are not immediately observable. Okay, so what other ways do we have? How do we actually learn these labels? How do we actually learn if people are truly qualified or unqualified? Okay, so one option is to wait for the outcome, but it could take months or years. Another option that kind of fits closely with the theme of this workshop is to rely on predictions. Okay, so these predictions could come from experts, like human experts, or they could come from more powerful auxiliary models. Okay. The issue with using the predictions is that they might be noisy and they might be costly. Okay, so here the idea is that like after doing the classification, we're not immediately and freely learn about the true label, but we can go through these predictions from the experts or powerful models to learn if this person is going to actually become successful or this person is going to actually repay their loan. The issue is that these are not free and these are not completely accurate. Okay. So if we change the setting to like, if we relax some of the assumptions that we made in the previous model to capture this more realistic setting, then the labels will become a limited resource. Okay, so we cannot like find the labels at each point in time. We need to be smart about like in what cases query a label, hire an expert, or use some expensive models. And the main challenge is when should we do that? When should we query a label? Okay. So this is going to bring us to a new setting where the labels are noisy, costly, and not always available. The agents are still strategic as we had in the first part. They're going to manipulate their inputs to receive the outcomes that they want. And now we need to be selective about when to query the labels of these examples. So our new goal is to learn a robust classifier to manipulation with minimal label queries, despite the noise in the labels and the manipulations of the agents. Okay, so this has become like much complicated. Okay, so this topic of having like when the labels are not immediately available or when the labels are costly is not something that we're inventing in this paper. It has been a well-established field in machine learning called active learning. So the main idea of active learning is to learn efficiently by querying only a small number of samples, by querying some informative samples and not all of them. Okay, and I have some references for this field in learning theory. Okay. And we also have strategic classification, as we talked about so far. We are learning in presence of agents who are manipulating their input. Okay, so we are now bringing these two fields. So to the best of my knowledge, active learning and strategic classifications have been two separate topics until recently. So we're now want to use ideas from both of these algorithms and come up with algorithms that are both robust to manipulation and are active learning. Okay. So let's see more concretely what is changing in our model. The first change is the label axis. So labels are no longer free. We are now actively finding labels, and this could be noisy. Okay, that's the first change. The second change that I'm going to change to the model is that I'm no longer going to assume that like the truly qualified and truly unqualified are separated or separated through a margin. Okay. So there will be some bounded noise, there will be some inseparability, and there is no margin anymore. So these two are kind of relaxations to the previous model that we studied. The third change that we're making to a model is a distributional assumption. So we're adding a distributional assumption over the original values of the points. This is a limitation compared to the previous case, but in all active learning literature, you need some distributional assumptions. Otherwise, like if you do worst case analysis as we did in the first part of the talk, then it's always possible that the labels that you're not picking are like the more informative ones. So we're going to now assume that the original feature vectors are coming from some distribution, specifically a uniform distribution over a unit ball. Okay. And agents are strategic as before. They want to manipulate to maximize their utility. Okay. So let's see this more formally. So again, I have a similar slide to what we had before. Let's see exactly what we're changing with this new model. Again, we're running this over time. At each point in time, the learning algorithm is going to announce its qualification rule. Next, an applicant is going to come. The applicant has some original features or true features. They may take some actions and have some modified features that the algorithm is going to see. The same utility model for the agents, getting a benefit of 1 for being classified positive minus the cost that they are paying to move. So like one of the changes is coming up here. So the original data points are no longer linearly separable. They are almost separable, and there is no longer a margin. Okay. So the majority of them are like 1/2 space, and the majority of the positive points are in 1/2 space. The majority of the negative points are in the other half space. There is some amount of inseparability or noise. So it depends on how you want to model that. For example, you can think that these points are truly separable, but our prediction model is noisy. Okay. Another way to think about it is that these points are actually not completely separable. So there are some true positives among negatives, and there are some true negatives among positives. Okay. The true features of the points are going to be distributed uniformly. And the algorithm, again, is going to decide positive or negative based on its classification rule that it has in the first step and the features that it sees. And this time, the algorithm is going to selectively request for labels and update if it has made a mistake. Okay. And our new goal becomes to minimize the number of mistakes, but at the same time also minimize the requested labels because they're costly. Questions about this new model?
So is it by criteria or is it some of the two or?
It's by criteria, yeah. Okay, so what are our technical contributions? We give an efficient active learning algorithm for classification of strategic agents. If we compare to the results from part 1, it extends them to have some label noise or inseparability in the data. And if to compare it to the active learning literature, we're now handling the strategic aspects of agents, and at the same time, we're matching the best known bounds for label and query complexity. Okay, and we are kind of combining these two fields that have been mostly in isolation before. Okay. So similar to the first part of the talk, I'm going to briefly tell you about the original, like the non-strategic model, and then the changes that we make. How much time do I have? Yeah, that's great, thanks. Okay. So we're going to, as our baseline, we're going to use an algorithm that was designed for non-strategic setting, but it was an active learning algorithm with noisy input. Okay. And that algorithm was also a version of the Perceptron algorithm. So there are like many similarities between the algorithms that we saw in the first part of the talk. There are two key ideas to this algorithm. Okay, so the first idea is like how we do the updates. So the update rule for this algorithm is going to be different from the one that we saw in the first part. More specifically, we're going to do the updates such that at each point in time with each update, we're getting closer to the true classifier. Okay, so like just to add a bit of technicality, in the first part, we were just like always improving our dot product with the true classifier. In this part of the talk, we are minimizing, we are like reducing the angle. Okay. Another idea of this paper or the like algorithm for active learning in non-strategic case is using query labels in a narrow margin. Okay, so let me explain it in a picture. So let's say that like this is the ball that our data can come from. Okay, this is our current classification, like weight vector. So we're going to classify everything that's in the upper half as positive. So we're not going to always ask for labels, right? So we're going to like see some points and then we're going to see some point and we're going to classify them at each point in time. Depending on where we see the points, we're sometimes going to ask for their labels. So the way that Jan and Jean decided on selectively querying the labels was they defined a margin, and whenever the data point that's observed is inside this margin, they're going to query the label. If not, they're not going to query the label. Okay. So what is the idea? The idea is that as we go along with our algorithm, then the points that are very far from our decision boundary, the points that are in this area, we're already probably classifying them correctly. Okay. And the points that are very close to the decision boundary, even if we're making some mistakes on them, they're not going to change our boundary so much. So they're not going to make us improve the current classification rule by a lot. Okay. So that's the intuition of like how we can just focus on a narrow band for doing our queries and still do well. Okay. I'm going to briefly show you, like, give you the main ideas that they use and then how we adapt them to work in the strategic case. So the easiest way to think about it is that there is an outer loop and an inner loop. So this slide is their outer loop. So basically they're going to they're going to start with some initial vector for classifying as positive or negative. And then they're going to, in the inner loop, run another algorithm that always makes the next vector closer to the decision boundary. And they're going to make this margin that I showed you on the last slide narrower and narrower as we go on. Okay. So how does the inner loop work, which is like the main part? Okay, so basically we're going to have a limit on the number of samples that we're going to see. Okay. We're going to start by observing samples. So again, this is not a strategic case. So everything that we see is their actual position. Okay. And we're going to classify everything as everything that we see with the current vector that we have. until the point that we observe is in the band that I showed pictorially. Okay. If they are within a band, we're going to query their label. If we have made a mistake, we're going to update our classifier based on the true label of the point. Okay, so it's kind of very similar to the original perceptron algorithm that we saw, except that here we are like kind of just getting the true label for the feature vectors that are within a band. Okay. And then after doing each of these inner loops for a certain number of time, we're going to go back to the outer loop, and then we're going to shrink the size of the margin. Okay, and at the end, we're going to convert to the true classifier. All right. So how do we change this algorithm to work for the strategic setting? So this is, again, like similar to the first part. We had some algorithm that worked very well in the non-strategic case. It was efficient. It made a small number of mistakes. But if you can come up with examples that, like, if you run this algorithm without making any changes, it's going to do very bad in the strategic scenario. One of the changes that we're making to the algorithm to update it for the new setting is very similar to before. It's a threshold adjustment. So we're no longer going to classify everything with a dot product as positive. We're going to have a higher threshold. Okay, so that like whenever we converge, the truly qualified points are either on the correct side or can get themselves to the correct side, and people who are unqualified are too far from the decision bound. So the next change that may be more interesting and is kind of different from the previous part is that, so, okay, so let me first explain like how do we define our query margin, okay? So our query margin is, in the picture, it's going to be very similar to their algorithm, except that we're only going to query labels within that band that we have classified as negative. Okay. Why is that helpful? So for a point that has been classified as negative, the utility maximizing action was not to manipulate. Okay, so basically with the way that I define the utility maximizing structure of the applicants, if an applicant is going to be classified as negative, they're not going to manipulate. Okay, so if I ask for a label for an agent who has been negatively classified, I know that it's like, this is exactly the true feature vector of that agent. Okay, so if I quickly go here, so we're still like doing something closer to this picture, except that this is for the part that is like on this side, that we would classify them as negative. Okay. And the idea is that although we are focusing on this narrow band and only for people who have been classified as negative, because of the distributional assumptions, this still gives us representative samples. Okay. The last change, the last modification is the update rule. So like in the first part, we only needed a classification rule and an update rule. Here we need classification rule, label query rule, and update rule. And our update rule is very similar to the non-strategic setting. Okay, so why? Remember that we only query labels for points that have been classified as negative. Okay. And these are the points for which we're going to learn if we had made a mistake or not made a mistake. And therefore, these are only the points that we're going to use for our update rule. Since these are classified as negative, they have not manipulated, so we can just use the features that we see from these points in the update rule, and it's going to be okay. Going to the algorithm just to show you our changes. So like some of them are very similar to the first part, adding this extra threshold for classifying the agents as positive. And the other part is we are defining the margin of a label query for the points that have been classified as negative. And we're only going to update whenever we make a mistake on a negative point, which means that we have classified this the true, this point was actually a true point. This point had label actually equal to 1, not -1. And we're going to update based on the features that we observe from this. Okay. Questions about this part? Good. Okay. So these are, this is our main theorem. So we are getting okay, so there's the assumption that the points, the true feature of the points are like have some bounded inseparability. So this could again be the noise in the prediction, or it could be the inherent inseparability of the points. Epsilon is our target error. So at the end, we want to find a classifier that disagrees with the perfect classifier with probability at most epsilon. So if the noise that we have in our data point has this relationship with the error that we're targeting, our algorithm gets these label queries, mistake bounds, and runtime. They are exactly the same as the non-strategic case, which is, I think, an interesting aspect of this result. And these bounds are pretty much efficient. So there are lower bounds for them known, even for the non-strategic case. Okay, all right. So the broader impact, especially of this second part of the talk, is that like we're doing more realistic assumptions about agents being strategic, having noisy data, and so on. If we use active learning, so we're getting like very efficient algorithms even with active learning, and that's kind of a maybe a paradigm that's observed in other active learning models, which is like if you limit yourself to only focus on part of data, surprisingly, sometimes it could be better than focusing on all of the data. And lastly, I mentioned that we are making this uniform distributional assumption. So it's not, our results are not tied to like this extreme assumption, even if we have like a distributional assumption for smooth distributions, the bounds are going to work. Okay, so let me conclude. So for this talk, we mainly focused on strategic classifications, classifying agents who may manipulate their input to get their desired outcome. In the first part, we focused on learning about the outcomes in a free way, not having any noise. And in the second part, we moved to a model where we could be active about like the points that we want to learn their outcome. We mentioned that we can use the information from the experts, either human experts or having predictions, which is something that we learned a lot today, and handle the noisy setting. And the technical contribution is combining both strategic aspects with active learning, and the result matches the best known label complexity results, as long as mistake bands and so on. For future work, I think it would be very interesting to come up with a framework for handling learning in strategic settings. So like I presented to you some stylized model today, and then for each of these algorithms, we needed to make, I don't know, slightly different changes. So it would be interesting to come up with a framework of like how we can do strategic learning or classify either classification or other learning objective that we have. And to have a wider model that would capture richer utility models, fairness, and many other assumptions. Thank you all so much.
We have time for like 2 questions. Yeah.
Thanks, Doc. In the first part, is there like a lower bound on kind of like the cost that any online algorithm has to suffer for like the online classification?
Right. So I think the bound from strategic from the classic Perceptron algorithm is tied for any deterministic algorithm.
And what is that bound? Like,
It depends on, okay, so it depends on, let's say you have your points are like in a ball of radius r, and then there's this margin of gamma, like it's the r over gamma squared, I think. Yeah. Because like it makes sense if you like scale everything, you should still get the same number of steps.
Thanks.
Any other questions? Yeah.
Hey, is there any natural way that you could extend this to non-linearly separable data?
Okay, very good question. I don't think there's, okay, so the second part is still a work in progress. So it may, we haven't figured, like we haven't thought about it for the second part. For the first part, we thought about it for some time, and I don't think there's a natural way. Okay, so there could be like an impossibility result, but we don't know.
Okay, yeah.
Thank you.
So if I understand correctly, in your strategic active learning version, it's important for you to initialize your perceptron from a place where everything is classified as negative, for example, right? Or is there a difference between the non-strategic and strategic with respect to that? Because you're only using samples that are classified in a particular mistakes on a particular direction. So I'm wondering whether the initialization actually plays a difference in this.
Yeah, that's a very good question. I did not have the initializations on the slide, but it is not very different from the original case. So the way that the non-strategic initialization works is that like you start with two opposite vectors, and then you run them for some time, and then find like you pick the better out of these two for your like initial vector. And then with high confidence, you can prove that this is the vector that you picked is going to be at most 90 degrees from the actual one, if that makes sense. So you're going to like pick two opposite ones, run each of them for some time, and then compare the mistakes that you've made along the way. And then you can prove that the better out of these two has actually like an acute angle with the two classifier. And then if we do our, so we also prove that this is the case for strategic set.
Okay, let's thank the speaker one more time.